Hello everyone. Today we will start a new session on multipulse transformers. Okay. So, this multipulse transformer we will have these contents like 6 pulse rectifier concepts, from which we will develop the 12 pulse star delta transformer and then zigzag transformers and extended delta transformers, okay, which can be used for the feeding the rectifiers of converters. So, why we need to study multipulse transformers? Now, many multi-level converters, not only multi-level converters, but many normal conventional 2-level VSI or VSC, they have the DC at the input. Okay. So, the DC bus is present on in such voltage source converters. Now, the question is how do we get that DC? We get that DC from an input AC supply, right. Of course, we can also get the DC from a battery or from other stiff DC sources, but in many of the multi-level converters we get the DC by rectifying the input AC supply. Now, these kind of multi-level converters, for example, can be used for a motor drives application, for example, and then we have an input fixed AC which is converted into a DC, and from the DC and using a voltage source inverter we can get a variable AC output which can be fed to the motor. So, AC to DC and then DC to variable AC. This is how the structure looks like. Now, in this part of the course we are focusing on the rectification part, that is AC to DC, that part. So, what has been popularly used for converting AC to DC is a 6 pulse rectifier, bridge rectifier 3 phase, which has been like a very popular choice for a long time now. Okay. And in this both thyristors and diodes can be used for converting the AC to DC. We can also have front end converters or PWM rectifiers at the AC to DC, but those are controllable switches, they require controllable switches. In many applications where we do not need the use of like variable DC supply, we simply use a diode bridge rectifier, 3 phase diode bridge rectifier, because diodes are much easy to construct and they do not require any control, they are uncontrolled devices. So, in many cases for the sake of simplicity we simply convert the AC into DC through a 6 pulse diode bridge rectifier. So, such 6 pulse diode bridge rectifiers have been in use for a long time and for a wide range of voltage and power, okay, starting from like converting from 230 volt single phase AC to 15 volt DC for low power electronics for some less than a watt or maybe tens of watts, and going up to like in the megawatt power range also. Okay. Now, if you see, so this is the 6 pulse rectifier. Okay. So, here you can see we have a input AC and we have a transformer, and then the transformer is fed through a 6 diode bridge rectifier, 3 phase diode bridge rectifier, and on this side we have a current source which is acting or which is representing the load. Okay. Now, usually we have the transformer here. Okay. The transformer is needed mainly for two purposes. Number one is that it isolates the AC sides from this side of the load. So, there is an electrical isolation because of the transformer, that is the number one. And number two is that in case of a fault on the DC side, for example, if there is a dead short circuit fault here, okay, on the DC side, then the leakage inductance of the transformer helps us to limit the rate of rise of the short circuit current. Okay. So, the transformer leakage impedance should be a certain value. For example, people typically choose transformers having leakage impedance say 5 to 6%, okay, typically 4 to 6% in that range, and it cannot be made very small because during the time of short circuit on the DC side, the transformer impedance is the element that limits the rate of rise of current. So, it plays an important role apart from isolation. Now, on the DC side we see that we have a very large inductive load which is represented by a current source here. So, we will continue with this because in most of the high power converter applications this may be a good representation of the actual circuit used. In some cases we also have capacitors here on the DC side. So, the analysis is slightly different, but on a similar strategy we can do the analysis with a similar strategy if we have a capacitor on the DC side, but in this course we will consider a current source at the load side. Okay. Now, this analysis is already very well covered in basic power electronics courses. I will not go into the details of operation of the diodes here. For example, you can see that diodes have a numbering here D1, D3, D5 and D2, D6, D4. So, there is a sequence of conduction of these diodes. So, D1 and D2 will first conduct and then D2 and D3 will conduct depending on the instantaneous line voltage magnitudes. Okay, whoever is at the peak, that pair of diodes will conduct. So, I will not cover that. What we will see more in this part is what happens to the output voltage and the input current. More specifically, the input current is something which we are going to study and which is our concern for this course and for multi-level converters. Now, why it is a concern, we will come to that. Now, let us first understand how is the output voltage waveform and the input current. So, the output voltage waveform is because of the sequence of conduction of the diodes, it typically looks like this. So, it is called a 6 pulse rectifier because there are 6 lobes in this fundamental cycle, and so if this is 360 degree, then each lobe is kind of like spanning 1/6 of 360 degree, that is 60 degrees. So, the peak to peak ripple here, so if this is 1 here, if this value is 1, that is cos 0, and so this value will be 30 degree, okay, because this total length is 60 degree. So, this is 60 degree here, and so half of it is 30 degree, and cos 30 degree or cos pi by 6 is equal to 0.866. So, therefore, the peak to peak ripple is close to 14%. There are 6 lobes, okay. That is why this is called a 6 pulse rectifier. Now, what is the input current waveform? So, if you take any phase, okay, suppose you take I A, the input current waveform typically looks like this. Okay, this is a quasi square wave waveform, and where for some time this is 0 and sometimes this is equal to the load current magnitude when the diodes are conducting. So, when D1 is conducting, this is a positive value, when D4 is conducting, it is a negative value. Okay. So, this is how, so this blue waveform here is how the input current looks like. Okay. And this input current, as you can understand from the waveform, is highly non-sinusoidal. It is far away from sinusoidal. Okay. It has a lot of harmonics present in it. Now, the input supply voltage is sinusoidal. Typically, we can assume that the input supply voltage is almost close to a perfect sine wave. Now, the input current drawn by this 6 pulse rectifier, as we can see here, is not at all sinusoidal. Okay, it is a quasi square wave. Now, this leads to poor power quality at the input. So, we are basically injecting a lot of harmonics into the supply. Okay. Now, as long as the magnitude of this current is less, the harmonics that we are injecting and which leads to the overall deterioration of the input current is reasonable, or it is under control if the magnitude of the load is small. But for many high power application, the magnitude of the load is quite significant. Okay. So, in that case, the amount of harmonics or the degree of pollution that we are injecting into the supply, that can be quite high, that can be substantial, and this will lead to a lot of input current harmonics and consequently poor power factor. Okay. So, which will lead to an overall deterioration of the input supply voltage quality, okay, which can be supplied to other loads. Okay. So, it can cause flicker, it can cause unwanted disturbances to other loads, etc. So, there are some standards like IEEE 519 or IEC 61000, where the standards say that if you build a converter, then the maximum amount of harmonic that this converter can inject into the supply, there is a limit to that maximum value. Okay. So, typically like IEEE 519 says that something called as THD is there, we will explain that THD, that should be less than 5%, okay, of the input current. So, we need to devise some strategy to improve the input current quality, okay, or reduce the harmonics in the input current. So, this is what we will study here. Okay. So, we can use multipulse rectifiers to improve the quality of the input current. Right. So, before going that, so let us analyze quickly what are the harmonics present in this waveform, okay, so that we can at least know what are the harmonics that are getting injected into the supply. So, this is a periodic waveform, and so if you write the Fourier series, this is very standard notations. So, this is A0 an cos n omega t and Bn sin omega t, and from observation we see that A0 is 0. This waveform has odd symmetry because f of omega t is minus of f of minus omega t. So, this means here whatever is happening f of omega t, a minus of omega t here, the negative is happening. So, therefore, we can say that n terms are 0, and also it has half wave symmetry. You can see that f of omega t plus pi, that is whatever is there, is minus of f of omega t, or what is happening here. So, therefore, only odd terms in Bn are present. So, therefore, we can now find out what is Bn, because An is 0 and A0 is equal to 0, and so Bn is equal to, you can do this integration, and then you find 4I by n pi cos n alpha, where alpha is the angle at which the square wave below alpha the square wave value is 0, quasi square wave value is 0, after alpha the quasi square wave value is I. So, the magnitude of harmonic, so we can write f t as 4I by n pi cos n alpha sin n omega t. So, this is the Fourier series expansion of this quasi square wave, where n is equal to odd. So, we see that we have all the odd harmonics present here. Okay. So, in this case, in the case of a the input current drawn from the 6 pulse rectifier, the value of alpha is equal to pi by 6, as you can see here. So, if you put f t there cos n alpha, so you put n pi by 6, and then if you put the values of n as 3, 5, 7, 11 like that, we find that all these 5th, 7th, 11th, 13th, 17th, 19th, in general 6n plus minus 1 harmonics are present in the input current waveform here. So, these are all these harmonics, okay, will be injected into the supply. Okay. So, this is the like the Fourier spectrum 5th, 7th, and the magnitude of the nth harmonic, as you can see, is proportional to 1 by n. Okay. So, the harmonic, the contribution of the harmonic of course is more if we have like 5th and 7th, their contribution is predominant, rather than if you go to the higher spectrum, their contribution goes down. Now, as I said, for low power application this may be sometimes acceptable, because the total contribution of this harmonic is not so great, but when you go for say megawatt applications, the harmonics, the contribution of the harmonic is quite substantial, and we have to take care of this harmonic. So, one way of taking care of this is like using multipulse transformer, that is more than 6 pulse transformer. Okay. So, we will study one of these multipulse transformer, that is the 12 pulse transformer, and then subsequently higher pulse transformers also. Okay. So, before I go into that, let me also say that let me also quantify certain, we will put some definitions like distortion factor. So, distortion factor is kind of like a measure of harmonics. Okay. So, distortion factor of input current is defined as the ratio of the RMS value of the fundamental component to the total RMS amplitude. So, distortion factor is the fundamental RMS divided by the total RMS, okay, in the presence of harmonics. Okay. So, this is one definition, distortion factor. Then another definition which is frequently used, total harmonic distortion. So, what is total harmonic distortion? It is, so it is defined as like this. So, basically it is the contribution of all the harmonics as a percentage of I1, that is as a percentage of the fundamental. Okay. So, it is the contribution of all the harmonics that you can see here, I2 square plus I3 square plus up to In square divided by I1. Okay. So, this is another quantification of harmonics which is present in the input current. So, THD and distortion factor, they are related to each other. So, you can just put the values. So, 1 plus THD square is 1 by df square. Okay. You can see this relationship. And there is also one more definition, that is called the input displacement factor. So, the displacement factor of the input current is defined as the cosine of the angle between the fundamental component of AC current and the fundamental AC voltage. Okay. So, fundamental AC voltage and fundamental current, the angle between them, cosine of that angle is called DPF or distortion power factor. Okay. So, the power input, okay, is V1 I1 into distortion power factor. Note that this voltage we are assuming to be almost very close to a sine wave. So, the harmonics in the voltage are not so significant. So, we can assume that the input voltage is a perfect sine wave without any harmonics. So, the power flow from the supply is because of the fundamental component of current and the DPF. Okay. Other higher harmonics of current will interact with the fundamental voltage, but the net average power will be 0 for the higher harmonic current components. Okay. If we had a voltage which also has harmonics, then the voltage harmonics and the current harmonics will also cause a power flow. But most of the cases we see that the voltage is almost like a pure sine wave, the supply voltage. So, it will, so the power delivered to the load will be the interaction between the fundamental voltage and the fundamental current and the DPF. So, that is what is written here, P in is V1 I1 into DPF. So, the input power factor is defined as the ratio of the total input power to the total RMS volt ampere. Okay. So, the power factor is P in divided by V RMS into I RMS. Now, V RMS is same as V in V1. So, P in by V1. So, if I can substitute P in by V1, and what is I RMS is distortion factor divided by I1 from the definition of distortion factor. So, therefore, power factor is equal to DPF into DF, that is power factor, input power factor is distortion power factor into distortion factor. Okay. And this is this relationship is noted because you see the effect of harmonics is not only to inject, that means the effect of harmonics also deteriorates the power factor. Okay. So, harmonics affect the input current quality as well as the input power factor. So, therefore, we need some methods to address this issue. Okay. Now, there are several strategies. So, we will talk about the multipulse rectifier, that is more than 6 rectifier in reducing the harmonics. Okay. Now, there are several other types of strategies, other types of techniques to mitigate harmonics. Okay. Like you can also have active filters and others, but they are essentially a component which is outside the converter. Okay. So, means that if you build a converter, it is desirable that the converter is kind of like self sufficient on its own in terms of the input side current which is drawing from the supply. Okay. What I mean to say is that the input current drawn by a converter ideally should be such that it meets all these standards like IEEE 519 or IEC 61000 standards. So, therefore, the converter must have some technique inside it, so that the input current which is drawn from the supply is more or less free from harmonics or very less in harmonics. So, that is why for large power converters we go for a multipulse rectifiers. Okay. The concept of 6 pulse or the concept of multipulse rectifier, 12 pulse rectifier or 18 pulse or 36 pulse rectifier, these concepts have been taken from AC to DC rectification. Okay. 12 pulse rectifiers have been in use to have better quality of DC voltage. Okay. Wherever we used to convert from AC to DC, 12 pulse rectifiers have been quite very well established. For example, the DC bus of an NPC, okay, the NPC has a if you recollect, the NPC has a DC bus. That DC bus can be fed from a 12 pulse rectifier. Okay. The 12 pulse rectifier has a substantially improved harmonic performance as compared to the 6 pulse rectifier. Okay. So, the advantage of multipulse rectifier is that there are two advantages mainly. So, it reduces the input current harmonic distortion and it also improves the DC voltage ripples. That means, it minimizes the DC voltage ripple of the rectifier in case of a 12 pulse rectifier. So, in this course we will focus more on this factor, the input current harmonic distortion. Okay. So, this is the one which is more of concern in this course. Okay.